Good morning, students. So we will discuss today regarding the various microscopy we are using in nanotechnology, such as a scanning electron microscopy, a transmission electron microscopy, as well as atomic force microscopy. Let us see one by one these things. First, in the case of scanning electron microscopy, which is developed in the year of 1938 with the help of a rastering electron beam by the scientist named as Van Ardenne, and later in the year of 1942 the SEM started using for a bulk sample, and lastly in the year of 1965 it has been commercialized by Cambridge Scientific Instruments. Some of the informations we will be fetching with the help of the scanning electron microscopy are topography, means the surface features of an object can be taken, as well as the morphology, means the shape as well as size of the particles can be known. The composition, that means the elements or the compounds which are used for making the object, that can also be known. And crystallographic information, means the arrangement of atoms inside the object, right? So these are the parameters or the characteristics which we are going to know by using the scanning electron microscopy. The various components of SEM includes the electron gun, right? So the topmost portion will be the electron gun, which is going to emit the electrons, and will be having series of lenses which is used for controlling the diameter of the beam, because we need the intense radiation, so the diameter can be controlled with the help of various lenses, and the aperture can also be controlled with the help of a series of apertures, otherwise it is going to affect the properties of the beam, right? And now all this setup can be maintained in a high vacuum levels, right? Without any disturbance, outside atmospheric disturbance, we are going to maintain at a higher vacuum levels, right? So this is electronic beam sample interaction. We can observe these two diagrams. In the first diagrams, the first one, it is for low accelerating voltage, and this is for medium accelerating voltage, and the third one is for higher accelerating voltage, right? By these three things, what we can conclude is the interaction volume. We can see the interaction volume here, which is lower, which is little bit higher, and which is more higher, right? The interaction volume increases with increase in accelerating voltage. Similarly here, these are the graphs for atomic numbers, right? The interaction volume increases here by decreasing the atomic number, or vice versa, right? So this is how the incident electron beam is scattered with the help of sample that may be elastically scattered or inelastically scattered. The first component of scanning electron microscope is electron guns, right? So with the help of this electron gun, we are going to get electrons per time per unit area, which should have a high current density as well as the lesser electron spot, that means lesser area. Two types of electrons we can see here, a thermionic electron gun as well as field emission gun. In case of thermionic electron gun, the electrons are emitted with the help of a solid material such as a tungsten wire as well as a lanthanum hexaboride, right? So in the first one, we can observe the lanthanum hexaboride crystal. With the help of this crystal, it is going to emit the electrons. And in the second case, which is a cold gun, the first one was a hot gun and this one is a cold gun, which emits again the electrons with the help of a stronger electric field. with the help of stronger electric field, it is going to emit the electrons, right? So as well as we will get the smaller spot and high electrical density compared to the thermionic guns. That is the advantage of this field emission gun. Next one is vacuum. In case of SEM, we need chemical as well as thermal stability for a well functioning of the filament. That means we need a sufficient amount of inside pressure. In case of a field emission gun, we require 10 raised to power of minus 10 torr, and in case of lanthanum hexaboride, we require 10 raised to minus 6 torr. That is the amount of pressure we require in the case of SEM. The signal electrons must travel from sample to the detector, which is called as a chamber pressure, and in order to control this chamber pressure, that again depends upon the various types of detector. How much vacuum that is required, that again depends upon the different types of detectors. Next one, how it works. As I said initially, it uses the electrons instead of the light as in the normal case, right? So at the top we will be having the electron gun, which is going to emit the electrons, which can be made to travel in a vertical direction towards the downside with the help of various aperture as well as with the help of various lenses, and it is going to be focused on the specimen. When the electron beam hits the sample or the specimen, the secondary electrons as well as the scattered electrons are going to be emitted, right? So those electrons are going to be detected with the help of a detector. This is the detector, and the signal will whatever we are getting from the sample is very low, and that can be amplified with the help of amplifier, and again the amplified signal can be fed to the display through which we are going to get the image. And this is the image showing how the incoming electrons is going to strike the sample and what are the different rays, backscattered rays will be getting, right? So this is the incoming electrons beam, and after impinging or striking on the surface of the specimen, will be getting the backscattered electrons, secondary electrons, auger electrons, X-rays as well as cathode luminance, right? So now regarding secondary electrons, which is having the lower energy, that has to be ejected from the K shell of the specimen, which is the outermost specimen of the atom, by inelastic scattering interaction with the beam electrons, right? So due to their low energy, these electrons originate within a few nanometers from the sample surface. These are having a lower energy. The important one is here the backscattered electrons, which consists of the higher energy electrons originating in the electron beam that are reflected or backscattered out of the specimen interaction volume by elastic scattering interaction with the specimen atoms, right? So it is used for heavier elements. It is used for heavier elements, which is heavier means which is having higher atomic number, backscatter electrons more stronger than the light electrons, means low atomic number, and thus appears brighter in the image. How to prepare the samples? So first we should go for taking the appropriate size of the sample which should fit in the specimen chamber. The specimen can be mounted rigidly on the specimen holder. It is called as specimen stub. In the diagram, whatever we are going to see is that is aluminum stub, which is going to hold some of the specimens. For imaging in the SEM, the specimen must be electrically conductive as well as it should be electrically grounded. These are some of the the steps for preparation of the sample: cleaning the surface of the specimen, stabilizing, rinsing, dehydrating, drying the specimen, mounting the specimen, coating the specimen. First we should clean the surface which contains soil, mud, dust, etc. Next one, stabilizing it. If it is of a dry hard material such as wood, bone, feather, dried insects or shells, that can be examined with little treatment. It won't require much treatment. But for living cells, tissues, soft bodies, we require chemical fixation to preserve and stabilize their structure. Stabilization is typically done with fixatives. A fixation is nothing but it is some chemical. We are using glutaldehyde as well as aldehydes. In addition to that one, we are also using formaldehydes, osmium tetroxide, tannic acid as well as thiocarbonhydrazides. Rinsing the specimen. The sample must be rinsed in order to remove excessive fixatives. Next one, we are going to remove the moisture content or the water content from the specimen, that is called as dehydration. After that one, we are going to dry it completely, otherwise the sample is going to be destroyed. Next one, it has to be mounted with the help of a mounting holder, and it has to be mounted properly with the help of specimen stub. The charging up. The charging up is a phenomenon where the negative charge of the incident electron beam accumulates on the surface of a non-conductive specimen, and the potential in the beam incident area changes to cause various image troubles. That means whatever the incident beam will be having, that is IP, that should not be equal to ISC, that is secondary electron incident rays, and IBSC, that is backscattered electron incident rays, as well as the absorbed, right? It should not be equal to the sum of all those things. That is called as a charging up, right? So this is the difference what we can observe between the destroyed one or the disturbance due to the charge up, and this is the regular one. The charge up phenomenon can be prevented by coating the non-conductor sample with a metal conductor, right? In case of non-conducting material, we are going to keep some of the charging or the coating materials. Here in this picture, we have a thin coating of around 20 to 30 nanometers, right, which is going to eliminate the charge up phenomenon. See here, the electrons are going to move from, and these electrons are connected to the ground. As I said, the thin coating layer can be maintained of 20 to 30 nanomicrons, right? So these are some of the conductive materials what we are having: gold, palladium alloy, platinum, osmium, iridium, tungsten, and sputter coater. Sputter coater is nothing but it is the instrument which is used for coating the non-conductive surfaces. So it is one example, the spider, which is coated with the help of gold. Some of the advantages we are having: it gives a detailed 3D and topographical image. It works very fast. A modern SEM allows for the generation of data in digital form, and most SEM samples require minimum preparation, that means for metallic preparation. Some of the disadvantages also will be having: it is very expensive and a large, that is nothing, bulkier in size. A special training is required to operate the scanning electron microscopy. Preparation of the sample can result in artifacts limited to only solid samples and carry a small risk of radiation. Because of the electrons, we are having some radiation problem also. These are some of the applications of SEM: virology, cryo-electron microscopy, 3D tissue imaging, forensics, SEM rendering detailed 3D images. So this is what regarding the scanning electron microscopy.